Today, we are going to cover the second subtopic of topic 2, work, energy, and power, called energy. Kinetic energy and potential energy storage and transfer. An object may have energy due to its motion, kinetic energy, or its position, potential energy, and that energy may be transferred and stored. A moving object has kinetic energy. The faster an object moves, the greater its kinetic energy. This is because energy had to be transferred to an object to get it moving when a force had acted on it. And more energy would be needed to get something to move faster. If you lift an object upwards, you give it gravitational potential energy. Higher an object is, the greater its GPE. If you let the object fall, you can get the energy back again. This is an example of transfers from GPE to kinetic energy. So there's a force acting on it to put it in its highest point, and the car now has maximum GPE. But then this also means that kinetic energy equals 0. Then when it drops, the GPE is transferred into kinetic energy and the car speeds up. Back at the lowest point, maximum kinetic energy and GPE equals 0. The car has enough kinetic energy, though, to continue up the next slope. It slows down when it goes up because it's losing kinetic energy and gaining gravitational potential energy. Kinetic energy and gravitational potential energy expressions. Recall and use the expressions kinetic energy joules equals 1/2 times mass in kilograms times velocity meters per second squared. Gravitational potential energy in joules equals mass in kilograms times g, which is 10 newtons per kilogram on Earth, times height in meters, like height from the ground. Speed before something hits the ground. I will show you a video of how to calculate this.
So I want to try doing a couple of questions that are about how to answer specific types of question. And this type of question is something that's come up in exams a few times before, and it's usually the same sorts of mistakes that students make. So I want you to try and avoid making those mistakes, and hopefully if a question like this comes up in the exam, then you'll be able to get all the marks for it. So if we read the question through first, and then I'll tell you some of the reasons that people fall down usually. So a 600 gram ball is dropped from a height of 3.2 meters. What is its speed just before it hits the ground? So the first thing that I would always get you to do is to think about what values are we actually given in the question. And we're told that it's a 600 gram ball. So the first thing that I would do is I would write what this means. And this is 600 grams is mass, except that we don't do mass in grams, we do mass in kilograms. So you need to convert this. So 600 grams in kilograms is 0.6 kilograms. So even before moving on, I would think to myself, we don't use grams, we use kilograms. Let's do the conversion so that I don't forget. It then tells me that it is a height of 3.2 meters. So straight away, I already know that that's a height. And actually that's a bit of a clue for what we're about to do. And then it says, what is its speed just before it hits the ground? Now, the most common mistake with this sort of question is that people say, oh, it's asked me to calculate speed. I know that the equation for speed is speed equals distance divided by time. I've got something in meters, so that's a distance, but I haven't got a time. I don't know how to answer this question. And actually, whilst you are calculating speed, you need to think about other words that mean a similar thing to speed, and that is velocity. And it's actually the velocity that we want to be looking at, because that's what we want to find in one of our equations. And like I said before, this word height is important, because when we're talking about height, there is one equation that we really need to think about. But first of all, we're going to write down what we've got, because that's really good practice for calculation technique. So we've got a mass of 0.6 kilograms, and we've got a height of 3.2 meters. And then it's asked me for a speed or for a velocity. So I'm just going to write velocity equals question mark. That keeps us a bit focused about what we need to do. If you think about the equations that you've used, there is one equation that links mass and height, and that is the equation for gravitational potential energy. So you might have seen it as GPE. I'm going to write it as E with a little p like that. And the equation for gravitational potential energy is mass times small g times height. And mass times small g is the weight of an object. And we should know that we can do that by 0.6, which is our mass, times g, which at GCSE we say is 10, and the height, which is 3.2. So if we work this out, so 0.6 times 10 times 3.2, we get an answer of 19.2 joules because it is potential energy. Next, the assumption that we need to make is that all of the potential energy is going to be converted when it's dropped. So it's going to have this potential energy at a height of 3.2 meters. It's then going to drop. And you should know that whenever anything is dropped, we have potential energy being converted into kinetic energy. So this is the assumption we are going to make. So with our list here, we could add that the potential energy, because we've calculated it, is 19.2 joules. We can then assume that therefore its kinetic energy, by the time it gets to the bottom of its fall, is also 19.2 joules, because all of this potential energy will have been converted into kinetic energy. And then we can think about, well, actually, I know that the equation for kinetic energy does contain velocity. So we can write that out, that our kinetic energy is 1/2 times mass times velocity squared. And this is how we can calculate our velocity. Now you could rearrange this algebraically to start off with, or you can substitute in the values and then solve for v. So we're gonna do that because it tends to be a little bit easier. So if we put down our values that we know directly below the equation, our kinetic energy is 19.2, and then we've got 1/2 times our mass of 0.6 times v squared. And I'm actually going to try and bunch these two up. So we're going to consider 1/2 times 0.6 a bit of a block. So we want to get v squared by itself. So what we're going to do is we're going to divide both sides by 1/2 times 0.6. So we'll end up with 19.2 over 1/2 times 0.6. If you've been shown a little bit of a different method for rearranging the kinetic energy equation to find V, then do whatever you find is easiest. But it's just trying to keep the algebra simple for some people. So 19.2 over 1/2 times 0.6 will equal V squared. Okay, you need to make sure that you've got your brackets in here. So if we do this on the calculator, we've still got 19.2. So we're going to do divided by 0.5 times 0.6. And this is going to give us 64. Now we're almost there, but we need to remember that 64 is actually V squared. So therefore, we need to do the square root of 64 will give us V. And this will be 8. So, I know that, but you know, the square root of 64 is 8. So therefore that's 8 meters per second that this ball will be traveling at just before it hits the ground.
Give and identify examples of changes in energy that have occurred as a result of an event or process. Chemical. Fuels like petrol or coal are stores of chemical energy. When these fuels burn, the stored energy is released, usually as heat and light. Elastic. Metal springs of a car are always storing and releasing elastic energy when it travels, so that occupants have a smooth ride. Nuclear. Radioactive materials are stores of nuclear energy. The energy is stored in the tiny positively charged core of the atom. Thermal. When you go near a hot object, you may feel thermal energy. This is energy traveling from a hotter object to a colder one. Light. Very hot objects glow brightly. They are giving out light energy which radiates outwards all around the hot object. Sound. Energy can be transferred to an object surrounding as sound energy. An electric current brings electrical energy to a loudspeaker. Sound energy is produced. Electrical. An electric current carries electrical energy. When the current flows through a component such as a heater, it gives up some of its energy. Energy transfer by forces, electrical currents, heating, and waves. Transfer by forces, mechanical working. Here I have an example. The massive ball of a demolition machine possesses mechanical energy, the ability to do work. When held at height, it possesses mechanical energy in the form of potential energy. As it falls, it exhibits mechanical energy in the form of kinetic energy. As it strikes the structure to be demolished, it applies a force to displace the structure. It does work upon the structure. Electric currents, electrical workings. Electric current is a convenient way of transferring energy from place to place. Electricity may be generated in a power station many kilometers away from where energy is required. Heating. No matter how good the insulation, energy is transferred from a hot object to its cooler surroundings. Waves. Light waves reaches us from the sun. That is how energy is transferred from the sun to Earth. Some of the energy is also transferred as infrared and ultraviolet radiation. These are all forms of electromagnetic waves. Principle of conservation and efficiency. The principle of conservation of energy states that in any energy conservation, the total amount of energy before and after the conversion is constant. The efficiency of an energy conversion is the fraction of the energy that ends up in the desired form. Example of situation that combines both. So here's an example of a situation that combines both. Like I said before, a lamp. This is the Sankey diagram of the lamp. Electrical energy is converted into light energy and heat energy. As you can see here, principle of conservation of energy is shown as it was 100 joules of electrical energy before, and after it was converted, there was 75 joules of light energy and 25 joules of heat energy. Energy before and after conversion is equal. Now, another idea or concept is efficiency. A lamp, what's useful from a lamp? We use a lamp for light. So the fraction of energy that ends up in the desired form is light energy. Unless you're into heat, like that's your thing. But in most cases, it's light energy. So to calculate the efficiency of this lamp, we have to go useful energy, which is light, divided by total energy input, which is 100 joules. So 100 J. Then we divide that, that's equal to 0.75. Then we have to times it by 100 to get a percentage. And that's equal to 75%. So our lamp is 75% efficient.